is Arumugalakshmi. Today we are going to discuss the problems in lesson 10 Oscillations of class 11 physics. First problem. Consider the Earth as a homogeneous sphere of radius r and a straight hole is bored in it through its center. Show that a particle dropped into the hole will execute a simple harmonic motion such that its time period is t is equal to 2 pi into square root of r by g. So here the oscillations of a particle dropped in a tunnel along the diameter of the earth is SHM. This we have to prove. Consider the earth to be a sphere of radius r and the center is found to be O. A straight tunnel is dug along the diameter of the earth. Let g dash be the acceleration due to gravity at the surface of the earth. Suppose a body of mass m is dropped into the tunnel and it is at the point r at the depth below the surface of the earth at any instant. G dash is the acceleration due to gravity at p. And we know that g dash is equal to g into 1 minus d by r. That is the formula for variation of acceleration due to gravity due to depth. This formula we have already discussed in lesson 6. So here it will be g dash is equal to g into r minus d divided by r. Here if y is the distance of the body from the center of the earth, then r minus d is equal to y. So the equation becomes g dash is equal to g into y by r. The force acting on the body at the point P is given by F is equal to minus m into g dash according to Newton's second law. Here substituting the g dash value, we get the expression as minus mg by r into y. From this equation we infer that the force is directly proportional to the displacement. The negative signs indicates that force acts in the opposite direction of the displacement. Hence, from this relation, we can understand that this is a SHM. Thus, the body will execute SHM with the force constant K is equal to mg by r. So, the time period is given by 2 pi into square root of m by k. Now, substituting the k value, we have 2 pi into whole square root of m divided by mg by r. Get cancelled. So, the expression for time period becomes t is equal to 2 pi into square root of r by g. The second problem. Calculate the time period of oscillation of a particle of mass m moving in a potential u is equal to half k x squared where x is less than 0. We know the expression for force from potential energy as F is equal to minus du by dx. Substituting the u value, we have F is equal to minus d by dx of half kx squared. So we have to differentiate this expression. So before differentiating, we will take the constant outside. Here the constant is half k. So taking it outside, we get minus half k into d by dx of x squared. D by dx of x squared is nothing but 2x. So the expression becomes minus 1 by 2 k into 2x. 2 get cancelled and the expression for force is F is equal to minus kx. According to Newton's second law, F is equal to ma. So comparing these two equations, the LHS is equal, so we can equate the RHS. So the equation becomes ma is equal to minus kx. From this we can get an expression for acceleration as a is equal to minus kx by m. Now, the acceleration of a particle in SHM is given by a is equal to minus omega squared x. So, comparing these two equations, we have minus kx by m is equal to minus omega squared x. So, omega squared is equal to k by m, which implies omega is equal to square root of k by m. From this, we can find the expression for time period as t is equal to 2 pi by omega. So substituting the omega value, we have t is equal to 2 pi into square root of m by k. Now the third problem. Consider a simple pendulum of length L is equal to 0.9 meter, which is properly placed on a trolley rolling down on an inclined plane which is at an angle theta is equal to 45 degree with the horizontal. Assuming that the inclined plane is frictionless, calculate the time period of oscillations of the simple pendulum. So here the length of the pendulum L is given as 0.9 meter. It is inclined at an angle theta is equal to 45 degree. We are supposed to find the time period. Time period is given by T is equal to 2 pi into square of L by G dash, where G dash is equal to G cos theta. Since it is inclined at an angle theta, we are including G dash as G cos theta. So substituting this value, we have T is equal to 2 pi into square root of L by G cos theta. Substituting the pi value, small g value, theta value, we have 2 into 3.14 into square root of 0.9 divided by 9.8 into cos 45. So substituting the values and simplifying, we get the time period as 2.263 seconds. The fourth problem. A piece of wood of mass m is floating erect in a liquid whose density is rho. If it is slightly pressed down and released, then it executes a simple harmonic motion. Show that its time period of oscillation is T is equal to 2 pi into square root of m divided by a g rho. We know the spring factor of the liquid K is given by a rho g. This is the formula for spring factor. The inertia factor is given by m. So the expression for time period is T is equal to 2 pi into square root of inertia factor divided by spring factor. So substituting the values, we have T is equal to 2 pi into square root of m by a rho g. The fifth problem. Consider two simple harmonic motion along x and y axis having the same frequencies but different amplitudes as x is equal to a sin omega t plus phi along x axis and y as y is equal to b sin omega t along y axis. Then show that x squared by a squared plus y squared by b squared minus 2xy ab cos phi is equal to sin square phi. And also discuss the special cases when phi is equal to 0, phi is equal to pi, phi is equal to pi by 2, phi is equal to pi by 2 and a is equal to b, and last case is phi is equal to pi by 4. So first let us prove the expression x squared by a squared plus y squared plus b squared minus 2xy ab cos phi is equal to sin square phi. Then we shall substitute the special cases. So first let us write the expression for x and y separately. X is given as x is equal to a sin omega t plus phi and y is given as y is equal to b sin omega t. Now one small rearrangement. The phase difference between x and y is 5. So how we are writing the expressions of x and y is as follows. X is written as a sin omega t and y is written as b sin omega t minus 5. When you write in this way also, the phase difference is also 5. So it can be written in this way. So from this equation, x is equal to a sin omega t will be equal to x by a. Similarly, from the equation y is equal to b sin omega t minus 5, cos omega t, the expression is square root of 1 minus sin square omega t. Sin omega t is given by x by a. So substituting that value here, we will get cos omega t is equal to square root of 1 minus x squared by a squared. Now we will start the derivation with the expression for y. Y is equal to b sin omega t minus 5. Here this b which is in the RHS, I am taking that to the LHS. So the expression becomes y by b is equal to sin omega t minus 5. Now see this RHS, it is in the formula sin a minus b. So sin a minus b, the expansion is sin a cos b minus cos a sin b, where a is equal to omega t and b is equal to 5. Now using this expansion, we get y by b is equal to sin omega t cos phi minus cos omega t sin phi. Now here instead of sin omega t, we will substitute as x by a, and cos omega t we will substitute as square root of 1 minus x squared minus a squared, which we had already found. So substituting this expression, we have y by b is equal to x divided by a into cos phi minus square root of 1 minus x squared the whole divided by a squared into sin phi. Second term. See the second term in the RHS. Second term we keep it as it is. The first term in the RHS I am taking it to the LHS. So the expression becomes y by b minus x by a cos phi is equal to minus square root of 1 minus x squared by a squared into sin phi. Now squaring on both the sides, we have y by b minus x by a cos phi the whole square is equal to 1 minus x squared by a squared into sin square phi. Here in the LHS, it is of the formula a minus b the whole square. So expanding using the formula, we get a square plus b square minus 2ab, where a is y by b and b is x by a into cos phi. So using this relation, we get y squared by b squared plus x squared divided by a square cos square phi minus 2y divided by b dot x divided by a into cos phi, which is equal to 1 minus x squared divided by a squared into sin square phi. Now simplifying the equation, we have y squared by b squared plus x squared by a squared into cos square phi minus 2xy divided by ba into cos phi is equal to 1 minus x squared by a squared into sin square phi. Now in the RHS, we take the sin square phi inside the bracket. We are going to multiply the sin square phi inside each term. So the equation becomes y squared by b squared plus x squared by a squared into cos square phi minus 2xy divided by ab into cos phi is equal to sin square phi minus x squared by a squared into sin square phi. Now the second term in RHS, I am taking it into LHS. So it becomes plus x squared by a squared into sin square phi on the LHS. So the equation becomes y squared by b squared plus x squared by a squared into cos square phi plus x squared divided by a squared into sin square phi minus 2xy ab cos phi is equal to sin square phi. Now in the LHS, the second and third terms, we have x squared by a squared as common. So if you take that as common, inside the bracket you will have cos square phi plus sin square phi, which is equal to 1. Hence the equation becomes x squared by a square plus y squared by b square minus 2xy divided by ab into cos phi, which is equal to sin square phi. This is what we have to prove, and hence we have proved. Now let us substitute the cases. 5 cases are there. These 5 cases we are going to substitute in this last expression. Case 1. In case 1, phi is equal to 0. So if you substitute the angle phi is equal to 0 in this expression, cos 0 is equal to 1 and sin 0 the whole squared is equal to 0. So substituting, we get x squared by a squared plus y squared by b squared minus 2xy divided by ab is equal to 0. The expression in the LHS resembles the formula a minus b the whole square, where a is equal to x by a and b is equal to y by b. Hence the equation becomes x by a minus y by b the whole square is equal to 0, which implies x by a minus y by b is also equal to 0, which once again implies x by a is equal to y by b. So find an expression for y which becomes y is equal to b by a into x. So this is an expression for a straight line passing through the origin with positive slope. Now move on to the case 2. In case 2, phi is equal to pi. So substituting the phi value as pi, we have the equation x squared by a square plus y squared by b square minus 2xy divided by ab into cos pi. Cos pi value is minus 1, which is equal to sin square pi. Sin square pi, the value is once again 0. Hence the expression becomes x squared by a square plus y squared by b square plus 2xy divided by ab is equal to 0. The LHS of the equation resembles the formula a plus b the whole square is equal to 0, where a is equal to x by a and b is equal to y by b. Hence the expression becomes x plus x by a plus y by b the whole squared is equal to 0, which implies x by a plus y by b is equal to 0, which implies x by a is equal to minus y by b. So the expression for y becomes y is equal to minus b by a x. Rearranging the terms, we get this expression. This expression is the equation of a straight line passing through the origin with negative slope. Now we will move on to the third case. In third case, phi value is equal to pi by 2. So substituting this value in the expression, we know that sin pi by 2 is equal to 1, cos pi by 2 is equal to 0. So substituting that value, we get x squared by a squared plus y squared by b squared is equal to 1. And this is an equation of ellipse whose origin is the center. The case 4. Case 4, phi is equal to pi by 2 and the condition is a is equal to b. So when the condition phi is equal to pi by 2, we will get the same expression as x squared by a squared plus y squared by b squared is equal to 1. Here once again you have to substitute the answer as a is equal to b. So if you substitute that, we will get x squared by a squared plus y squared by a squared is equal to 1. Taking a squared as common and moving it on to the RHS, we have the expression x squared plus y squared is equal to a squared. And this equation is an expression for circle whose origin is at the center. Now the last case. In case 5, the angle phi is equal to pi by 4. So substituting this in the given equation, we have x squared by a squared plus y squared by b squared minus 2xy divided by ab into cos 45. It's equal to sin 45 degree the whole square. So substituting the value cos 45 and sin 45 value, which is equal to square root of 1 by 2, we get the answer as x squared by a squared plus y squared by b squared minus 2xy divided by ab into square root of 1 by t is equal to 1 by 2. And this is the equation of ellipse. So all the 5 cases are discussed. The sixth problem. Show that for a particle executing simple harmonic motion, the average value of kinetic energy is equal to the average value of potential energy. So first let us find the average value of period of oscillation. Then we will find the average potential energy for a period of oscillation. Then finally we will find the total energy. We know that the average kinetic energy is given by 1 by t integral of 0 to t ek into dt, which is equal to 1 by t integration 0 to t. Kinetic energy expression is given by half m omega squared a squared cos square omega t dt. So before integration, we will take the constant outside. The constant is half m omega squared a squared. So taking that outside, we have 1 by 2t m omega squared a squared integration 0 to t into cos square omega t can be written as 1 plus cos 2 omega t by 2. Now the 2 you have got in the denominator, that also has to be taken outside since it is a constant. So we have 1 by 4t m omega squared a squared into differentiating 1 with respect to t, we will have t plus cos 2 omega t differentiating, we have sin 2 omega t divided by 2 omega. So the limits is 0 to t. So when you apply the limits, we get the expression as half m omega square a square. This is the expression for kinetic energy. Now the average potential energy is given by 1 by t integration 0 to t ep dt. So substituting the potential energy expression, we have half integration m omega squared a square sin square omega t dt. Once again, before integration, the constants we are supposed to take it outside. So the expression becomes 1 by 2t m omega squared a squared integration 0 to t sin square omega t is once again written as 1 minus cos 2 omega t divided by 2 into dt. Now once again taking 2 which is in the denominator as a constant outside, we have 1 by 4Tm omega squared a square into, now differentiating we have t minus sine 2 omega t by 2 omega. The limits are 0 to t. So applying the limits, finally we get the expression as potential energy is equal to 1 by 4 m omega squared a squared. Next, we have to prove average potential energy is equal to average kinetic energy is equal to half total energy. So for this, we are starting our derivation from the expression for velocity. V is equal to dy by dt, which is equal to differentiating y. Y is equal to a sin omega t. Differentiating this with respect to dt, we have a omega cos omega t. So kinetic energy is given by half mv square. So squaring the expression, we have half m omega squared a square cos square omega t. Potential energy is given by half m omega square y square, which is equal to half m omega square a square sin square omega t. The total energy is got by adding these two. So we will have half m omega square a square cos square omega t plus half m omega square a square sin square omega t. Here the common terms are half m omega square a square. So taking that outside, we have half m omega square a square into cos square omega t plus sin square omega t. We know that cos square omega t plus sin square omega t, the value is 1. So the total energy is half m omega square a square. This expression can be written as 2 into 1 by 4 m omega square a square, which is nothing but the potential energy or kinetic energy. Hence, we have proved that the average value of kinetic energy is equal to the average value of potential energy, and it is equal to 1 by 4th of the total energy. The 7th problem. Compute the time period for the following system if the block of mass m is slightly displaced vertically down from its equilibrium position and then released. Assume that the pulley is light and smooth and strings and springs are light. So in this case A, you have got a pulley, one side is attached to a spring and the other side is attached to a mass. So when you just plug this mass and leave it, it executes a SHM. So the force acting is given by F is equal to ma according to the Newton's second law. Here the total force acting on these two strings is equal to F each. So the total force is equal to 2F, and due to the force, the extension produced is x by 2. So according to Hooke's law, we have F is directly proportional to the displacement. Here the displacement is x by 2 and the force is 2F. Hence the expression becomes 2F is equal to kx divided by 2. So from this, F is equal to kx divided by 4. So comparing this with Newton's second law, we have ma is equal to kx divided by 4. So finding an expression for acceleration, we have a is equal to k by 4m into x. So here acceleration is equal to some constant into displacement. So this is an SHM whose omega value is given by omega squared is equal to k by 4m. So omega will be equal to square root of k by 4m. Hence, substituting this omega value in the time period expression, we have t is equal to 2 pi by omega. Substituting the omega value, we have t is equal to 4 pi into square root of m by k. So for the first case, we have found the time period. We will move on to the second case. In second case, you have got a pulley is connected to a mass. At the top of the pulley, we have got a spring whose spring constant is k. So according to the Newton's second law, you have got F is equal to ma. Here the force acting produces an extension x. Hence F is equal to kx. So comparing these two equations, you have ma is equal to kx, where a is equal to k by m into x. So omega squared is equal to k by m and omega is equal to square root of k by m. Substituting this value of omega in time period, we have t is equal to 2 pi by omega. So t is equal to 2 by into square root of m by k. So this is the expression for time period.